Hello. I'm going to take a second tonight. Well, it's going to be more than a second. I'm going to take a few minutes tonight and talk to you about two problems from section 6.5. I'm going to discuss problems 12 and 13. Now, problem 12 is a direct application of the mean value theorem for integrals. It begins with the function is f of x equals 2x over 1 plus x squared, quantity squared, on the interval from 0 to 2. And part A says to find the average value of the function. Well, we know how to find the average value of the function. The average value of the function, we have a formula for that. That's the integral from a to b of f of x dx times 1 over b minus a. And so we use this formula here that we have in the book to find the average value of a function. Well, we know what f of x is. We're given that function. We know what a and b are. A is 0 and b is 2. So if we plug everybody in, this turns out to be the integral. Well, pardon me, it's 1 over 2 minus 0. So it's 1/2 the integral from 0 to 2 of 2x over 1 plus x squared, quantity squared, dx. Now that's a u substitution integral. We're going to have to do that with u substitution. In this case, u is going to equal 1 plus x squared. Du then is going to be 2x dx. And if you take a look at the integral that you've been given, you'll notice that you have a 2x dx given to you in the problem itself. So that integral with a simple u substitution turns out to be 1/2 the integral of u to the negative 2 du. So if we make that substitution, this turns out to be 1/2 the integral u to the negative 2 du. If we go ahead and integrate that, that becomes 1/2 1 over u to the negative 1. We add 1 negative 2, that gets us negative 1. And then we divide by negative 1, so that puts a minus out in front of everything. So our ultimate answer then is minus 1 over 2u. Now, 1 over 2u negative. There you go. There's the integral if you want to pause and take a look at that. Now when we resubstitute, that turns out to be minus 1 over 2 times 1 plus x squared. And we've got to evaluate that between 0 and 2. When we put 2 into this, we get negative 1/2 times. Putting in a 2, we get 1/5. Minus putting in a 1, putting in a 0, we get 1. So we get 1/5 minus 1. So that becomes negative 1/2 times negative 4/5. Or all in all, we get positive 4/10, or an answer of 2/5. Okay, 2/5. So there's the work there on the integral if you want to hit pause and take a look at that. So the average value of our function across the integral from 0 to 2 is 2/5. That's what we've determined. It's part B where we have to take a second and just think, what are they asking us to do in part B? In part B, it says find C such that f of C equals the average value of the function. Well, while it may not appear to be the mean value theorem for integrals, part B requires the mean value theorem for integrals. And what we know about the mean value theorem for integrals is we know this is true. We know f of C times the quantity b minus a is equal to the integral from a to b of f of x dx. That right there is the form of the mean value theorem that's in our book. I believe your author begins that sentence with the phrase, that is. It's the alternative form of the mean value theorem, and it's the form where we see that f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. That's the given form of the mean value theorem. But what do? They take the 1 over b minus a and they just move the b minus a to the other side. Now, I've drawn on the board for you a couple of times in class a representation that says, look, the area under the integral is the same as the area of a rectangle if the conditions of the mean value theorem are met. Well, if we just write a couple of words down here, below this formula, and we make a little sketch. Here's my function. Here's A. Here's B. If you take a look at this sketch, what we said in class is that integral represents that area. Well, if you look at the left-hand side of that equation, that's height times width. That's the rectangle. So the rectangle's on the left, the integral's on the right. The rectangle's on the left, the integral's on the right. So if we find the right-hand side, if we find that integral, which you and I just did, we found that integral. If we take a look up here, if we go all the way back up here to the top of the page, here's the 1 over b minus a. It's a half. 1 over b minus a is a half. So that means the integral itself, which we worked out all the way down here and got 2/5, the integral itself is whatever it was we were going to get before we multiplied by the half. Well, before we multiplied by the half, we were going to get 4/5. That means this integral right here, this integral is 4/5. We can redo the work. There's not really a point to redo the work, but if it's going to make you a little more comfortable, I know that the integral from 0 to 2 of 2x divided by 1 plus x squared dx, that's the left-hand side, integral a to b f of x dx. If we do the same u substitution, u is going to be 1 plus x squared, du is going to be 2x dx. We're again going to have the integral of u to the negative 2 du. Same integral we had before. We integrate u to the negative 2, we add 1. It's u to the negative 1. We divide by 1. It's minus 1 over u. So this gives us minus 1 over u. Now if we resubstitute in x, that becomes negative 1 over 1 plus x squared. Evaluated between 0 and 2, putting the 2 in there, we get negative 1/5 minus 2 squared is 4, plus 1 is 5, negative 1/5, minus, putting a 0 in there, we get negative 1, so that's plus 1. So our integral is 4/5. 4/5. The area of this shape right here is 4/5. 4/5. Here is 4/5. We found that. Now, what they're asking us is if this is 4/5, we know what b minus a is. B minus a is 2 minus 0. That's 2. So now, if you plug in what you know, you get an equation that looks like this. F of c, the thing we're looking for, we don't know what f of c is. F of c is equal to 2 minus 0. I'm sorry. F of c times 2 minus 0 is equal to 4/5. Well, f of c times 2, move the 2 to the other side. In other words, divide both sides by 2. You have 2 f of c equals 4/5. 2 f of c equals 4/5. Move the 2 to the other side. You get 2/5. F of c equals 2/5. Now, we got to understand what the question's asking us. The question says, all right, you know your function is 2/5. Somewhere between 0 and 2, that function they gave you is 2/5. Can you find that spot? Can you figure out where the function is equal to 2/5? Well, if we set up that equation, we know what the function is. The function is 2x over 1 plus x squared squared. Well, that looks fun. So we've got 2x over 1 plus x squared squared. That's f of x, f of c. And the question is, when is that going to be 2/5? Okay, when's it going to be 2/5? So this is what you end up with, this equation right down here. or my hand is over. Well, you know, that's an algebra equation. We can all work that out. We know what to do there. You can solve that. May not be fun, but you can solve it. If you solve that, you divide both sides by 2, cross multiply, expand, and solve. Okay. So that's problem 12. Now you just got to work out the algebra down there and find out what x is. And that value of x is going to be in your interval between 0 and 2 because the mean value theorem says so. All right, what about problem 13? Well, the next one. Problem 14. 14 looks just like, it's if you read it, it's an application of the formula for the average value of the function. 15 is finding the average value of a function, but instead of integrating, now you're going to use your friendly rectangles with midpoints. They brought those back again. And 17, the formula looks a little hairy on 17, but 17 is just use the average value formula. So 13 is a problem that offers us a bit of a challenge. If you read it, it seems like, really? So if you look at 13, 13 says you're given the integral from 1 to 3 of f of x dx equals 8. The integral from 1 to 3 of f of x dx equals 8. So draw that. You're integrating, so you know the function's continuous. You're integrating between 1 and 3, and the area is 8. So make a function that's above the graph, above the x-axis, pardon me. Put a line over here, call this 1. Put a line over here, call this 3. And this area is 8. Okay, the area is 8. Now remember, f is continuous. F is continuous. That's given. So here's what your picture looks like. Now you have no idea what this function is, right? We don't know what that is. It says f of x. I don't know what that function is. They're not even going to tell me what that function is. I don't even have to know what the function is, apparently, to solve the problem. So what am I supposed to prove? I'm supposed to prove that the value of the function here, this function touches 4. Somewhere this touches 4. That's what I'm supposed to prove. Where does that touch 4? Somewhere between here and here. Now, I don't even know the value of the function. If I knew the value of the function, I could go like this. I could go, well, you know, f of x equals 4. I could solve this. Solve f of x equals 4. And that would give me x. It would end up being between 1 and 3, and I would tell somebody, well, right there. There's where it happens. But the problem, if you look at it, it doesn't say find the x. That's not what it says. It says show that this is true. Show that the average, show that the function has to be 4 someplace. To put this in terms of real life, it basically says this. It says, if you know that your average speed to go from point A to point B, your average speed was 60 miles an hour, then you're guaranteed that at some point on your journey, you drove 60 miles an hour. Now, it may have only been for an instant. That speedometer may have said 60 for just an instant. But somewhere during that journey, your speedometer touched 60 miles an hour. You can't have an average speed of 60 without at some point on that journey going 60. Now, you may go 60 the entire trip, but we all know cars don't start at 60 miles an hour. So if you have an average speed on a journey at 60 miles an hour, you went faster than 60 miles an hour somewhere. Because there was a point in that journey when your car was parked and then you started down the street and you accelerated and you weren't going 60 instantaneously. So you were going 2 and then 5 and then 10 and then 15 and then later maybe 35. And then as you got onto the freeway, maybe you got up to 45 and 50 and 60. But if you average 60 miles an hour, then all of that time that you spent going slower than 60 miles an hour, that has to be balanced by some time when you were going faster than 60 miles an hour. mean, that just makes sense if you think about it rationally. Consequently, there was a place between when you began and when you finished this journey where you were going 60 miles an hour. That's what the mean value theorem for integrals says. It says somewhere, if you have an average, somewhere you had to be that value. So if we take a look at what we're given here, we're given that our function is continuous. And we're given an interval. The interval is from 1 to 2. That's A and B. A is 1, B is 2. If we just write down the mean value theorem, we understand that the hypotheses are satisfied. The hypotheses for the mean value theorem simply say the function is continuous. You have a continuous function because the problem gave you a continuous function. So here's what you know. You know there exists a C, an element of 1 to 3, such that f of C has to equal 1 over 3 minus 1, the integral from 1 to 3 of f of x dx. You know this is true. You know what I wrote there is true. There exists a C, an element of 1 to 3, such that f of C is equal to this. You know this is true because this is the conclusion for the mean value theorem. And the condition for the mean value theorem is met right here. Look, up here. Let's get it on the screen. There it is. F is continuous on the closed interval from 1 to 3. That's given in the problem. So how do I prove to you, how do I justify to you that this function equaled 4 someplace? Well, if you solve what we wrote down, 1 to 3, the integral from 1 to 3 of f of x dx, we're told that's 8. That's given. So that part of the equation is 8. We know that 1 over 3 minus 1, we know 1 over 3 minus 1 is a half. So we're left with this. If we read down here, this sentence says there exists a C in the interval from 1 to 3 such that f of C has to equal 1/2 times 8. Well, 1/2 times 8 is 4. So we just proved, using the mean value theorem, that somewhere in the interval, the function has a value of 4. Now, it may have 20 places where it has a value of 4 between 1 and 3. But that's not what they asked us. They asked us to show there's at least one. And we did. It happens at C. Now, we don't know where C is. Apparently, I know where my dog is. Hey, come here. What are you doing? How are you? You're interrupting. But you don't seem to care. No, you don't seem to care. Okay, I got to go back to work. Oh, thank you. That was loving of you. All right, bye. So we know that there's a place where the function, stop laughing. We know there's a place, he loves me. Somebody does. You knew well, okay, it's not a person, but at least something does. Of course, I feed him. I don't know that that really plays into the whole thing. We know there's a place where the function equals 4, and it happens at C, and while we don't know the value of that C, we know it's between 1 and 3, because the mean value theorem says so. Now, that problem 13, takes some thinking. All right? Listen to it again. Write some things down. Get yourself a picture. Here's all the things that I wrote down to try to convince myself that it worked. Pause the video, copy those on your paper, and as I go through it, read through those. Look at your notes. Look at this. Copy this down. And then as you listen to the video again, read each one of these lines as I discuss it and see if you can make this application of the mean value theorem of integrals something that you understand instead of something that mystifies you. All right, so that's it for tonight. Have a great time. I'll see you in class tomorrow.